Now we will demonstrate dynamic key generation on soft channel, which we will obtain by using Adam-Pluto, our software-defined radio platform. Adam-Pluto by Analog Devices offers a wide range of full duplex tuning from 325 MHz to 3.8 GHz, with a sampling rate of up to 61 megasamples per second, hence offering an instantaneous bandwidth of 20 MHz. The idea of software-defined radio is that the passband signals are directly translated to baseband signals, that is, centered around 0 Hz using a homodyne receiver. So SDR acts as a front end while all the processing on signal is done on the host system. Likewise, in case of a transmission, IQ samples or the baseband signals are synthesized by the host system and SDR up converts it to the passband. Adam Pluto interface easily with a MATLAB, one of the most friendly programming languages for researchers. So when we are in receiving mode, we receive IQ samples from the radio to the MATLAB interface, while when we are to transmit something, we synthesize appropriately modulated IQ samples on MATLAB and send it to the radio for a wireless transmission. So let us start the demonstration of dynamic key generation using received soft channel. Setup is as follows. UE1 and UE2 are willing to generate a key using correlated soft channel from Adam Pluto hardware. We have used this MATLAB code to trigger the channel and then estimate the received vectors. As these radios and host systems are not synchronized, we operate them in full duplex mode instead of operating them in time division duplex manner. We choose adjacent correlated frequency bands for full duplex operation. Radio on UE1 transmits a QPSK modulated signal on 2.1 GHz and radio on UE2 is tuned to listen to 2.1 GHz. Likewise, UE2 transmits a similar QPSK signal on 2.18 GHz while UE1 is tuned to listen to 2.18 GHz. As now we have access to the physical layer of the radio, we intentionally trigger the channel by popping different QPSK symbols, hence artificially creating the randomness in the channel. So this way of generating the key is known as precoding based key generation. So first we turn on the two transmitters by using transmit repeat function on MATLAB, and then we trigger the QPSK receiver, which are based on Simulink. So the baud rate is set to 400 kilo symbols per second and the packets are sent in burst mode. Each packet includes Barker code as a preamble for easy detection of the packet at the receiver. The blocks shown in the receiver diagram are taken from MATLAB communication toolbox. So these are some standard implementation of correcting frequency and phase offset using PLL and timing recovery circuits. We will now run the MATLAB code and will collect CSR samples. We will see a new file written named csr.csv on the current folder in MATLAB on both the screens. We will now use the same Zigbee platform to communicate the indices, syndrome, etc., as we cannot afford a bit flip at these phases. So we'll go back to our original Zigbee based console for key generation and we'll upload the CSR file instead of collecting the RSSI. The same process will follow starting from CSR sharing to UE1 for quantizer design, sharing of syndrome vector to UE2 for reconciliation, and finally we will get identical keys at the two node. We will then apply AES encryption and decryption to secure the image.